To the surprise of many students, statistics is a fairly significant part of a psychological education. To the surprise of no one, statistics is very rarely the favorite part of one's psychological education. Many psychology students hate statistics. For one thing, most have a non-mathematical background, which makes understanding complex statistical equations very difficult. After all, if you really love the idea of doing statistics, you probably be enrolled in a statistics program right now, not a psychology course. So, not surprising, there's a pretty large proportion of the student base that isn't very happy about the fact that psychology has so much statistics in it. You're probably wondering why you have to take statistics. It's possible that you didn't realize when you started your course that you'd have to know this much about statistics, but now find yourself inexplicably wading neck high through the Victorian sewers that is data analysis. The reason that you're in this mess that you find yourself in is because you have a curious mind. You might have asked questions like why people behave the way they do or why behaviors differ across cultures. What can we learn from rats in mazes? Will you get smarter by ingesting X amount of ginkgo biloba? Or does the law of attraction really work? Or are Filipinos naturally resilient? Whatever it is you're studying or researching, the reason you're studying it is probably because you're interested in answering questions. Scientists are curious people, and you probably are too. However, you might not have bargained on the fact that to answer interesting questions, you need two things: data and an explanation of those data. The answer to what the hell are you doing here, therefore, is simple. To answer interesting questions, you need data. Therefore, one of the reasons why your evil psychological statistics professor is forcing you to learn about numbers is because they are a form of data and are vital to the research process. But this explanation only leads to another perplexing question. Why do we have to go through all this trouble just to answer a question? My name is Dex Kamitan, a PhD student and lecturer at the University of the Philippines, a psychology professor at the Manila Titana Colleges, a big psychology nerd, and I will guide you through the bizarre yet important world of psychological statistics. Now, I thought that the right place to start might be to answer some of the more common questions that people have about stats. A big part of this issue at hand relates to the very idea of statistics. What is it? What is it there for? And why are scientists so bloody obsessed with this? These are all good questions when you think about it. So let's start with the last one. As a group, scientists seem to be very bizarrely fixated on running statistical tests on everything. In fact, we use statistics so often that we sometimes forget to explain to people why we do. This has been my issue back when I was an undergraduate psych student. No one actually explained to me why all these things are important. It's actually kind of an article of faith among scientists, especially social scientists, that your findings can't be trusted until you've done some stats. Undergraduate students might be forgiven for thinking that we're all completely mad because no one takes the time to answer one very simple question. It's a naive question in some ways, but most good questions are. There's a lot of good answers to it. But for my money, the best answer is a really simple one. We don't trust ourselves enough. We worry that we're humans and susceptible to all of the biases, temptations, and frailties that humans suffer from. Much of statistics is basically a safeguard. Using common sense to evaluate evidences means trusting gut instincts, relying on verbal arguments, and on using the raw power of human reasoning to come up with the right answer. Most scientists don't think this approach is likely to work. In fact, come to think of it, this sounds a lot like a psychological question to me. And since I do work in a psychology department, it seems like a good idea to dig a little deeper here. Is it really plausible to think that this common sense approach is very trustworthy? Verbal arguments have been constructed in language, and all languages have biases. Some things are harder to say than others, and not necessarily because they're false. For example, quantum electrodynamics is a good theory, but hard to explain in words. The instinct of our guts are not designed to solve scientific problems. They're designed to handle day-to-day inferences. And given that biological evolution is slower than cultural change, we should say that they're designed to solve the day-to-day problems for a different world than the one we're living in. Most fundamentally, reasoning sensibly requires people to engage in what we call as induction, making wise guesses and going beyond the immediate evidence of the senses to make generalizations about the world. If you think that you can do that without being influenced by various distractors, well, I have a bridge in Samar I'd like to sell to you. We can't even solve deductive problems once where no guesswork is required without being influenced by our pre-existing biases. Now, people are mostly pretty smart. Certainly smarter than the other species that we share the planet with, though many people might disagree. Our minds are quite amazing things, and we seem to be capable of the most incredible feats of thought and reason. That doesn't make us perfect though, and among the many things that psychologists have shown over the years is that we really do find it difficult to be neutral, to evaluate evidence impartially, and without being swayed by pre-existing biases. A good example of this is the belief bias effect in logical reasoning. If you ask people to decide whether a particular argument is logically valid, that is, conclusion would be true if the premise were true, we tend to be influenced by the believability of the conclusion even when we shouldn't. For instance, here's a valid argument where the conclusion is believable. Premise 1, all cigarettes are expensive. Premise 2, some addictive things are inexpensive. Conclusion, therefore, some addictive things are not cigarettes. Note how the argument is both valid and its conclusion believable. And here's a valid argument where the conclusion is not believable. All addictive things are expensive for premise number 1. Some cigarettes are inexpensive for premise number 2. Therefore, some cigarettes are not addictive as conclusion. The logical construction of argument 2 is identical to the construction of argument 1, and they're both valid. However, in the second argument, there are good reasons to think that premise 1 is incorrect, and as a result, it's probably the case that the conclusion is also incorrect. But that's entirely irrelevant to the topic at hand. An argument is deductively valid if the conclusion is a logical consequence of the premise. That is, a valid argument doesn't have to involve true statements. On the other hand, here's an invalid argument that has a believable conclusion. All addictive things are expensive for premise number one. Some cigarettes are inexpensive. Therefore, some addictive things are not cigarette. Note that this argument is invalid, but its conclusion is believable. So, finally, here's an invalid argument with an unbelievable conclusion. Premise number one states all cigarettes are expensive. Premise number two says some addictive things are inexpensive. And conclusion states, therefore, some cigarettes are not addictive. So now, suppose that people really are perfectly able to set aside their pre-existing biases about what is true and what isn't, and purely evaluate an argument on its logical merits. We'd expect 100% of people to say that the valid arguments are valid and 0% of people to say that the invalid arguments are valid. So, if you run an experiment looking at this, you'd expect to see data like this. If the psychological data look like this, or even a good approximation of this, we might feel safe in just trusting our gut instincts. That is, it would be perfectly okay just to let scientists evaluate data based on their common sense and not bother with this murky statistics stuff. However, you guys have taken psych classes before, and by now you probably know where this is going. In a classic study, Evans, Bartson, and Pollard in 1983 ran an experiment looking at exactly this. What they found is that when pre-existing biases, for example beliefs, were in agreement with the structure of the data, everything went the way you'd hope, like this. Not perfect, but that's pretty good, right? But look at what happens when our intuitive feelings about the truth of the conclusion run against the logical structure of the argument. What the fudge, right? That's not as good. Apparently, when people are presented with a strong argument that contradicts our pre-existing beliefs, we find it pretty hard to even perceive it to be a strong argument. People only did so 46% of the time. Even worse, when people are presented with a weak argument that agrees with our pre-existing biases, almost no one can see that the argument is weak. People got that one wrong 92% of the time. If you think about it, it's not as if these data are horribly damning. Overall, people did do better than chance at compensating for their prior belief. Since about 60% of people's judgments were correct, you'd expect 50% by chance. Even so, if you were a professional evaluator of evidence and someone came along and offered you a magical tool that improves your chances of making the right decision from 60 to say 95%, you'd probably jump at it, right? Well, of course you would. Thankfully, we actually do have a tool that can do this, but it's not magic. It is statistics. So that's reason number one why scientists love statistics. It's just too easy for us to believe in what we want to believe in. So instead, if we want to believe in the data, we're going to need a bit of help to keep our personal biases under control. That's what statistics does. Help keep us honest all the time. Now, in 1973, the University of California, Berkeley had some worries about the admission of students into their postgraduate programs. Specifically, the thing that caused the problem was that the gender breakdown of their admission looked like this. Now, given this, they were worried about being sued. Given that there are nearly 13,000 applicants, a difference of 9% in admission rates between males and females is just way too big to be coincidence. Pretty compelling data, right? And if I were to say that to you that these data actually reflect a weak bias in favor of women, well, sort of, you'd probably think that I was either crazy or sexist. Oddly enough, it's actually sort of true. When people started looking more carefully at the admission data, they told a rather different story. Specifically, when they looked at it on a department by department basis, it turned out that most of the departments actually had a slightly higher success rate for female applicants than for male applicants. This table shows the admission figures for the six largest departments, with the names of the departments removed for privacy reasons. Here's what's going on. Firstly, notice that the departments are not equal to one another in terms of their admission percentages. Some departments, for example, departments A and B, tended to admit a high percentage of qualified applicants, whereas others, for example, Department F, tended to reject most of their candidates, even if they were highly qualified. So, among the six departments shown here, notice the department that the Department A is the most generous, followed by Department C, then followed by Department B, then by Department C, then D, that order. Next, notice that males and females tend to apply to different departments. If we rank the department in terms of the total number of applicants, we get department, or rather, Department A will rank first, Department B will be ranked second, D will come in third, C will come in fourth, F will come in fifth, and E will come in last. The easy departments are, if you look at it, A and B. On the whole, males tend to apply to the departments that had higher admission rates. Now compare this to how the female applicants distributed themselves. Ranking the department in terms of the total number of female applicants, a quite different ordering will be produced. First, you have Department C, followed by Department E, then D, then F, then A, then B. In other words, what these data seem to be suggesting is that the female applicants tended to apply to harder departments. This effect is known as Simpson's paradox. It's not common, but it does happen in real life, and most people are very surprised by it when they first encounter it, and many people refuse to even believe that it's real. But it's very real, and while there are lots of very subtle statistical lessons buried in here, I want to use it to make a much more important point. Doing research is hard, and there are lots of subtle, counterintuitive traps lying in wait for the unwary. So, this brings us to reason number 2 why scientists love statistics and why we teach research methods. Because science is hard, and the truth is sometimes cunningly hidden in the nooks and crannies of complicated data. Before leaving this topic entirely, I want to point out something else really critical that is often overlooked in research methods classes. Statistics only solves part of the problem. Remember that we started all this with the concern that Berkeley's admission process might be unfairly biased against female applicants. When we looked at the aggregated data, it did seem like the university was discriminating against women. But when we disaggregate and look at the individual behavior of all the departments, it turned out that the actual departments were, if anything, slightly biased in favor of women. The gender bias in total admission was caused by the fact that women tended to select for harder departments. From a legal perspective, that would probably put the university in the clear. Postgraduate admissions are determined at the level of the individual department. And there are good reasons to do that. At the level of the individual department, the decisions are more or less unbiased. The weak bias in favor of females at the level is very small and not consistent across departments. Since the university can't dictate which departments people choose to apply to, and the decision making takes place at the level of the department, it can hardly be held accountable for any biases that those choices produce. That was the basis for my somewhat glib remark earlier. But that doesn't exactly tell the whole story. After all, if we're interested in this from a more sociological and psychological perspective, we might want to ask why there are such strong gender differences in application. Why do males tend to apply to engineering more often than females? And why is it the reversed for the English department? And why is it the case that departments that tend to have female application bias tend to have lower overall admission rates than those departments that have male application bias? Might this not still reflect a gender bias? Even though every single department in itself is unbiased. Well, it might if you think about it. Suppose hypothetically that males prefer to apply to hard sciences and females prefer humanities. And suppose further that the reason for why the humanities departments have low admission rates is because the government doesn't want to fund the humanities. If you think about it, PhD places, for instance, are often tied to government-funded research projects. Does that constitute a gender bias or just an unenlightened view of the value of the humanities? What if someone at a high level in the government cut the humanities fund because they felt that the humanities are useless chick stuff? That seems pretty blatantly gender biased. None of this falls within the purview of statistics, but it matters to the research project. If you're interested in the overall structural effects of subtle gender bias, then you probably want to look at both the aggregated and disaggregated data. If you're interested in the decision-making process at Berkeley itself, then you're probably only interested in the disaggregated data. In short, there are a lot of critical questions that you can't answer with statistics. But the answer to those questions will have a huge impact on how you analyze and interpret data. And this is the reason why you should always think of statistics as a tool to help you learn about your data. No more and no less. It's a powerful tool that at the end, it's a powerful tool to that end, but there's no substitute for careful thought. Now, I hope that the discussion earlier help explain why science in general is so focused on statistics. But I'm guessing that you have a lot more questions about the role of statistics, what role statistics play in psychology, and specifically why psychology classes always devote so many lectures to stat. So here's my attempt to answer a few of them. The first question is, why does psychology have so much statistics? To be perfectly honest, there's a few different reasons, some of which are better than others. The most important reason is that psychology is a statistical science. What I mean by that is that things that we study are people, real, complicated, gloriously messy, infuriatingly perverse people. The things of physics include objects like electrons. And while there are all sorts of complexities that arise in physics, electrons don't have minds of their own. They don't have opinions. They don't differ from each other in weird and arbitrary ways. They don't get bored in the middle of an experiment, and they don't get angry at the experimenter and then deliberately try to sabotage the data set. At a fundamental level, psychology is harder than physics. Basically, we teach statistics to you as psychologists because you need to be better at stats than physicists. There's actually a saying used sometimes in physics to that effect, that if your experiment needs statistics, you should have done a better experiment. Now, they have the luxury of being able to say that because their objects of study are pathetically simple in comparison to the vast mess that confronts social scientists. And it's not just psychology. Most social sciences are desperately reliant on statistics. Not because we're bad experimenters, but because we've picked a harder problem to solve. We teach you stats because you really need it. Okay, now the second question goes like this. Can someone else do the statistics? To some extent, yes, but not completely. It's true that you don't need to become a fully trained statistician just to do psychology. But you do need to reach a certain level of statistical competence. In my view, there's three reasons that every psychological researcher needs to be able to do basic stats. First, there's the fundamental reason. Statistics is deeply intertwined with research design. If you want to be good at designing psychological studies, you need to, at the very least, understand the basics of stats. Secondly, if you want to be good at the psychological side of the research, then you need to be able to understand the psychological literature, right? But almost every paper in the psychological literature reports the result of statistical analysis. So, if you really want to understand the psychology, you need to understand what other people did with their data, and that means understanding a certain amount of statistics. Thirdly, there's a big practical problem with being dependent on others to do statistics for you. Statistical analysis is very expensive. If you ever get bored and want to look up how much the Australian government charges for university fees, you'll notice something interesting. Statistics is designed as a national priority category, and so the fees are much lower than for any other area of study. This is because there's a massive shortage of statisticians out there. So from your perspective as a psychological researcher, the law of supply and demands aren't exactly on your side here. As a result, in almost any real life situation where you want to do psychological research, the cruel facts will be that you don't have enough money to afford a statistician. So the economics of the situation means that you have to be pretty self-sufficient. Note that a lot of these reasons generalize beyond researchers. If you want to be a practicing psychologist and stay on top of the field, it helps to be able to read the scientific literature, which relies pretty heavily on statistics. Lastly, if you would say, I don't care about jobs, research, or clinical work, do I need statistics? Well, now you're just messing with me. Well, still, I think it should matter to you too. Statistics should matter to you in the same way that statistics should matter to everyone. We live in the 21st century and data are everywhere. Frankly, given the world in which we live in these days, a basic knowledge of statistics is pretty damn close to a survival tool. So far, most of what I've talked about is statistics, and you'd be forgiven for thinking that statistics is all I care about in life. Well, to be fair, you wouldn't be that far wrong. But research methodology is a broader concept than statistics. So most research methods courses will cover a lot of topics that relate much more to the pragmatics of research design. And in particular, the issue that you encounter when you are trying to do research with humans. However, about 99% of student fears relate to the statistical part of the course. So I focused on the stats in this discussion, and hopefully I've convinced you that statistics matters, and more importantly, that it's not something to be feared. That being said, it's pretty typical for introductory research method classes to be very stat heavy. This is not well, at least usually, because the lecturers are evil people. Quite the contrary, in fact. Introductory classes focus a lot on the statistics because you almost always find yourself needing statistics before you need the other research methods training. Why? Because almost all of your assignments in other classes will rely on statistical training to a much greater extent than they rely on other methodological tools. It's not common for undergraduate assignments to require you to design your own study from the ground up, in which case you would need to know a lot about research design. But it's common for assignments to ask you to analyze and interpret data that were collected in a study that someone else designed for you, in which case you need statistics. And in that sense, from the perspective of allowing you to do well in all your other classes, the statistics is far more urgent. But you have to note that urgent is different from important. They both matter. I really do want to stress that research design is just as important as data analysis. However, while statistics has a kind of universality and provides a set of core tools that are useful for most type of psychological research, the research method side isn't quite so universal. There are some general principles that everyone should think about, but a lot of research design is very idiosyncratic and is specific to the area of research that you want to engage in. To that extent, that it's the details that matter. Those details don't usually show up in the introductory stats and research methods classes. So, statistics is an inevitable part of psychology. While this inconvenient truth might be difficult to swallow for a lot of us, it's important that as early as now we change the way we see it from a roadblock that prevents us from reaching our degrees to vehicle that allows us to get there. That's all for today. My name is Dex Kamitan, and thank you for watching.